A perfect ring of stars floats in the blackness of space. This is the Cartwheel Galaxy, a cosmic bullseye born from a cataclysmic collision. Its bizarre structure is just the beginning of a much deeper mystery. By the end of this journey, you will have explored 50 of its strangest phenomena, from ghostly intruder galaxies to stellar fireworks moving in slow motion. How did a violent impact create such a symmetrical ring, and what unseen forces are still shaping its destiny from within? What does it feel like to witness a galaxy rewriting its own story? The first strange phenomenon begins with a cosmic paradox. Violent destruction here gives birth to new worlds. When the Cartwheel Galaxy collided with its smaller companion, the impact did not just rearrange existing stars. It ripped colossal streams of gas and dust from the galaxy's outer edges, hurling them into the void. This expelled material did not simply drift away into nothingness. Instead, something incredible happened. Under the relentless pull of gravity, these scattered clouds began to collapse in on themselves. They coalesced into glowing, independent islands of stars, each one a newborn tidal dwarf galaxy. Think of it as a galactic parent wounded in a terrible accident, scattering pieces of itself that then grow into entirely new, smaller families of stars. These celestial orphans now orbit their massive progenitor, permanent reminders of the collision that both shattered and created. How bizarre that a single event of chaos can forge new, stable structures, entire galaxies born from the debris of destruction. This ring of fire is almost impossible to comprehend. It spans a distance so vast it makes our own Milky Way seem compact. The outer starburst ring of the Cartwheel Galaxy measures 150,000 light-years from one side to the other. To put that in perspective, if you could place our galaxy inside it, the entire spiral of the Milky Way would fit comfortably within the ring's circle with room to spare. This is not just a collection of stars, it is a single, coherent structure, a cosmic racetrack where star formation is happening at a ferocious rate. The sheer size of this ring presents a puzzle. When the smaller galaxy punched through the cartwheel's heart, you might expect the resulting shockwave to create a messy, uneven wave of star birth. Instead, we see this perfect, symmetrical ring of fire on a scale that is almost unreal. How does a wave of energy travel so far and organize itself so perfectly? It is like dropping a single pebble into a pond and watching the ripple expand for miles in a perfectly circular wall of water, a phenomenon that defies our simple models of galactic collisions. This ring is not a suggestion of new stars, it is a declaration, a universe-scale announcement of creation written in light. What force could possibly keep such an immense structure so perfectly intact? Deep within this perfect ring of fire lies a profound emptiness. Most spiral galaxies like our own Milky Way possess a brilliant, dense core, a crowded central hub of ancient stars. The Cartwheel Galaxy, however, presents us with a ghost at its center. Its core is unusually faint and diffuse, a pale and puffed-up cloud of stars that lacks the sharp, brilliant concentration astronomers expect to find. This is the mystery of the missing central bulge. It is as if the heart of the galaxy has been scattered. The leading theory points directly to the Great Collision. When the smaller intruder galaxy punched through the cartwheel's center, its gravitational influence may have acted like a colossal stirrer, violently churning up the dense cluster of stars at the very core. This immense disturbance could have flung countless stars outward, effectively dismantling the tight central bulge and smearing its population into a much larger, far dimmer sphere. Imagine a tightly packed crowd of people suddenly hit by a powerful, invisible force that pushes them all away from the center, forcing them to occupy a much larger, emptier space. The crowd is still there, but its density is gone. This galactic disruption created a void at the center of a ring of furious creation, a quiet, expanded core surrounded by a storm of new stars. Why did the collision create such vibrant structure in the ring, yet leave only a pale echo where the galaxy's heart should be? This beautiful symmetry is only an illusion. Look closer at the cartwheel and you will see its skeleton is crooked. Radiating inward from the blazing outer ring are great, dark spokes of cosmic dust and cold gas. These are not the perfect, evenly spaced spokes of a bicycle wheel. They are twisted, uneven, and distinctly off-center, connecting the ring to the ghostly inner hub in a lopsided arrangement. This is the galaxy's hidden asymmetry, the lasting imprint of a catastrophic blow that landed at an angle. The pattern of these dark rivers tells a story of a violent, glancing impact. If the smaller galaxy had struck the cartwheel's core dead-on, the resulting shockwave might have created a perfectly symmetrical set of structures. But the evidence written in these dusty spokes suggests a different reality, a collision that was far from a direct hit. The smaller galaxy likely came in at a sharp angle, its gravity tearing through the larger disk and kicking up these immense waves of debris in a chaotic, unbalanced fashion. Imagine throwing a stone into a pond not straight down but at a sharp, slicing angle. The ripples that spread out would not be clean circles, they would be messy, uneven, and distorted. That is precisely what we are seeing in the cartwheel skeleton. These crooked spokes are the frozen ripples of that ancient, skewed collision, a permanent record of the precise violence that reshaped an entire galaxy. Why did such a messy impact ultimately create such a perfect ring of fire, while leaving these crooked scars as a permanent reminder of the chaos? Scattered across this galactic wheel are points of light that burn with an invisible fire. These are not ordinary stars, but ultraluminous X-ray sources, and their presence in such great numbers defies all expectation. An ultraluminous X-ray source, or ULX, is an object in space that emits a staggering amount of energy, but only in the X-ray part of the spectrum. This is light our eyes cannot see, a radiation far more energetic than the visible light from stars. To produce such intense and focused power, these objects must be devouring matter at a ferocious rate. Each one is likely a black hole or a super-dense neutron star locked in a violent dance with a companion star. The black hole's immense gravity pulls gas from its stellar partner, and as that gas spirals inward at nearly the speed of light, it heats up to millions of degrees, glowing with the searing brightness of X-rays. In a typical galaxy, you might find a handful of these cosmic furnaces, yet within the cartwheel they are everywhere, shining like dozens of brilliant, hyperactive beacons. Their unusual abundance is a direct consequence of the Great Collision. That violent event triggered a firestorm of star formation, not just ordinary stars, but also the births of the massive, short-lived stars that quickly collapse into these very black holes and neutron stars. Now, surrounded by the dense clouds of gas and young stars the collision left behind, these cosmic predators have an all-you-can-eat buffet. They are feasting on the galaxy's turbulent aftermath. Their incredible X-ray glow a direct measure of the chaos that created them. How many more of these hidden monsters are lurking within the ring, silently burning with the energy of a million suns? The furious ring of fire is not a static structure. It is a wave in motion, a slow-motion shockwave of star birth propagating relentlessly outward through the galactic disk. This is not a single, ancient burst of creation frozen in time. Instead, it is an ongoing chain reaction, a cosmic domino effect playing out across tens of thousands of light years. Imagine a stone dropped into a pond of gas and dust. The initial splash was the collision itself, and the first, most brilliant ring of stars is the leading edge of that ripple, but the wave does not stop there. As it expands outward, it compresses the gas it encounters, triggering the birth of a new generation of stars just behind the initial front. This creates a sequence, a timeline of stellar adolescence written in light. The oldest, redder stars are left in the wave's wake, while the youngest, bluest, and most brilliant stars mark its current, advancing edge. It is as if the galaxy is constantly recreating its own magnificent ring, one slow motion pulse at a time. This propagating wave solves one mystery while creating another. It explains the ring's incredible sharpness and coherence, but it forces us to ask what fuels this continuous expansion. What primordial reservoir of gas is this wave moving through, and how long can this magnificent, slow-motion firework display possibly last? The brilliant ring of the Cartwheel Galaxy tells a story of a catastrophic impact, but the perpetrator of this cosmic crime is nowhere to be found. This is the mystery of the ghostly intruder galaxy, the small companion that is believed to have plunged through the Cartwheel's heart. Identifying the exact culprit, however, is a profound challenge for astronomers. The scene is crowded with suspects. Several smaller galaxies linger in the same region of space, a galactic group where such close encounters are more likely. But which one was responsible for the hit and run? The evidence is largely circumstantial. The perfect ring and distorted core are the undeniable signs of a violent collision, yet the forensic trail has gone cold over hundreds of millions of years. The guilty galaxy would not have emerged unscathed. Such a tremendous impact would have ripped stars and gas from the smaller intruder as well, stretching it into long, faint streams that are incredibly difficult to detect against the vast, dark backdrop of space. It might now be a shredded ghost, its identity all but erased, simply absorbed into the larger structure of the cartwheel itself. Or perhaps it was flung away by the force of the encounter, a celestial projectile sent careening into the void, forever carrying the scars of the impact it caused. We are left with a cosmic whodunit, a beautiful galactic wreckage, and the lingering question of what became of the architect of its stunning transformation. Embedded within that vast ring of fire are jewels of unimaginable density. The Cartwheel Galaxy is not merely forming stars, it is constructing stellar metropolises known as superstar clusters. These are not the loose, glittering star associations we see in our own galactic neighborhood. Each one is a tightly packed city of stars, a sphere of space so dense it contains millions of newborn suns all bound together by gravity. In a typical galaxy, such extreme clusters are rare events, the result of once-in-an-eon conditions. Yet here they are everywhere, scattered across the ring like a string of cosmic pearls. Why is the cartwheel such a prodigious factory for these extreme objects? The answer lies in the unique physics of the collision's shockwave. As that colossal ripple of energy expands, it does not simply nudge the galactic gas. It slams into vast, primordial clouds with unimaginable force, compressing them to densities far beyond what is normally possible. This is not a gentle squeeze, it is a violent galactic-scale stampede of gas and dust. Under this extreme pressure, entire clouds collapse not into single stars, but into these monolithic clusters, forging millions of stars in a single, breathtaking event. Imagine the difference between a gentle rain that forms puddles and a catastrophic flood that carves out entire new lakes in an instant. The collision was that flood, and the superstar clusters are the deep, permanent lakes it left behind. Each one is a snapshot of the most intense star-forming conditions the universe can produce. What will become of these stellar cities in a billion years? Will they remain as dense relics, or will they slowly dissolve, their stars spreading out to join the galaxy's general population? The very fabric of the ring tells a story of cosmic alchemy. While the cartwheel's outer ring blazes with the light of new stars, its chemical composition reveals an even deeper mystery. The mix of elements out there is not what astronomers would typically expect from a star-forming region. There is an unusual abundance of certain heavier elements, the kinds of metals forged only in the hearts of the most massive stars and scattered by their violent deaths. This points to a nucleosynthesis process happening at a breakneck pace and on a colossal scale. Nucleosynthesis is simply the cosmic factory that builds all the elements in the universe, starting from the primordial hydrogen and helium created in the Big Bang. Normally, this is a slow, gradual process spread across generations of stars. But here, the collision created a perfect storm. It triggered the birth of countless massive stars, each one a frantic, short-lived factory fusing hydrogen into heavier elements like oxygen, carbon, and silicon. These stars live fast and die young, exploding as supernova in a mere few million years. Their cataclysmic deaths then blast these newly forged metals back into the surrounding gas, enriching it at an astonishing rate. The ring is not just forming stars, it is a self-contained, hyper-efficient recycling plant. It forms a generation of metal-rich stars, which then explode and seed the next wave of star formation with an even richer supply of building blocks. This creates a strange and lopsided chemical signature, a ring far more metallic than the galaxy's faint, ancient core. What does it mean for a galaxy to have such a chemically divided personality, with a primitive heart surrounded by a sophisticated, metal-rich wheel of fire? This brilliant glow comes at a terrible cost. The same starburst ring that makes the Cartwheel Galaxy so spectacular also creates a galaxy-wide bath of lethal radiation. Every one of those millions of newborn massive stars is a frenzied engine, burning its nuclear fuel at a breakneck pace and pouring ultraviolet light and X-rays out into space. This is not the gentle, life-giving warmth of a star like our Sun. This is a continuous, searing blast of energy so intense it would rip the atmosphere from any fledgling world and scour its surface clean. Imagine standing not in sunlight but directly in front of a colossal industrial ultraviolet lamp, one powerful enough to illuminate an entire city. Now multiply that by millions and you begin to understand the hostile environment within that beautiful ring. This high radiation environment poses a profound challenge to the very possibility of planets, at least as we know them. The process of planet formation requires calm, cool clouds of gas and dust to gently coalesce around young stars. But here, the fierce radiation pressure from all those brilliant suns acts like a cosmic blowtorch, pushing that raw material away, preventing it from ever clumping together into planets. It effectively sterilizes entire regions of the galaxy, creating vast zones where the seeds of new solar systems are vaporized before they can even take root. The Ring of Fire is, in a cosmic irony, a desert for worlds. It forges stars at an unbelievable rate, but in doing so, it may be destroying the very nurseries where life could one day emerge. What does it mean for a galaxy to be so creative and yet so destructive at the very same time? This rapid spin is not just a detail, it is the galaxy's very heartbeat. The Cartwheel Galaxy is whirling through space at a velocity that defies its appearance, spinning far faster than any tranquil pinwheel should. This strange and rapid rotation is a ghost in the machine, a direct inheritance from the ancient collision that gave the galaxy its form. When the smaller intruder plunged through the Cartwheel's heart, it did not just deliver a blow, it delivered a tremendous dose of angular momentum. Think of angular momentum as the cosmic essence of spin, the same principle that makes a figure skater whirl faster when they pull their arms in. During the collision, the smaller galaxy's own motion, its speed and trajectory, was not simply absorbed and vanished. Instead, its spin was transferred, like one spinning top striking another and setting it into a frantic new dance. This transferred energy sent the entire galactic disk spinning with a ferocious speed it never possessed before. The result is a galaxy caught in a whirlwind of its own making, its outer regions hurtling around the center at speeds that help maintain the ring's incredible, coherent structure against the relentless pull of gravity. How long can this dizzying cosmic dance last before the galaxy begins to slow? And what will become of its perfect ring when the spin finally fades? That beautiful ring is not a single event but a living timeline. Astronomers have uncovered a strange and telling pattern within its brilliant light. The stars are not all the same age, they are laid out in a perfect sequence, a stellar history book open for us to read. This is the phenomenon of the age gradient, a fossil record of the collision's ongoing shockwave. The very youngest, hottest, and bluest stars are concentrated on the ring's outermost edge. Just behind them, you find slightly older stars that have begun to cool and redden, and further in, the stars are older still. This progression is the undeniable signature of a wave in motion. Imagine a forest fire spreading across a vast plain. The leading edge is a wall of the most intense, brilliant flames, the point of active burning. Just behind that front, the fire has passed, leaving behind smoldering embers and charred wood. The outer ring of the Cartwheel Galaxy is exactly that, a cosmic fire front. The shockwave from the collision plows through the galactic gas like a plow through soil, compressing it and triggering the birth of brilliant new stars right at its leading edge. As the wave moves outward, it leaves behind the slightly older stellar generations, their location marking where the wave passed millions of years before. This gradient allows us to not just see the ring, but to read it. We can trace the shockwave's path backward in time, directly back to the moment of impact at the galaxy's center. How many millions of years does it take for that wave to cross from one side of the ring to the other? And what will happen when it finally runs out of galactic gas to fuel its expansion? A spiral galaxy is defined by its graceful, winding arms, a signature of orderly motion and gentle density waves. The Cartwheel Galaxy possesses none of this. Its previous identity, likely a stately spiral similar to our own Milky Way, was completely erased in the collision. That event did not just bend or distort the old arms, it effectively hit a cosmic reset button, scrambling the galaxy's entire structure into something entirely new. This places the Cartwheel in a unique morphological class, a ring galaxy, a category defined by the very act of its own destruction. Think of a spiral galaxy as a beautifully organized city with clear, curving boulevards guiding traffic. The collision was like a meteor strike in the city's central square, sending out a shockwave that obliterated all the old streets and forced the entire population to rebuild in a single, massive, circular highway on the outskirts. The old city plan is gone, replaced by a radical new layout born from pure chaos. This total transformation forces us to ask a deeper question about galactic evolution. Is a galaxy's form a permanent identity, or is it merely a temporary phase, vulnerable to being completely rewritten by a single chance encounter with a neighbor? The Cartwheel's smooth disk, devoid of any spiral trace, is a powerful testament to the universe's capacity for violent reinvention. But the galaxy's fire is not just written in starlight. A deeper, invisible heat permeates the Cartwheel, a thermal signature so intense it baffles astronomers. Observations in the infrared part of the spectrum reveal the presence of cosmic dust heated to extreme, almost unimaginable temperatures. This is not the typical, frigid dust floating between stars. This dust is superheated, glowing with a fierce thermal energy that points to something far more violent than mere starlight. Normally, interstellar dust is lukewarm, gently warmed by the diffuse light of many stars. Here, however, it is as if someone has taken a blowtorch to the galaxy. The dust is being blasted by an intense, concentrated source of energy from within the ring itself. What could possibly produce such focused, searing heat on a galactic scale? The prime suspects are the very same ultraluminous X-ray sources and the countless superstar clusters we have already encountered. Think of a black hole feasting on a companion star, or a dense cluster of 1,000,000 young, massive stars. Their combined radiation output is not just visible light. It is a torrent of ultraviolet and X-ray energy that slams into the surrounding clouds of fine dust grains. This is not gentle warming, it is a continuous high-energy assault. The dust absorbs this furious radiation and re-emits it as a brilliant, pervasive infrared glow, turning the entire ring into a colossal cosmic radiator. This tells us the galaxy's violent activity is not just on the surface, it is baked into its very fabric, heating it from the inside out. How much raw energy is required to keep an entire galaxy's dust this hot? And what does this relentless thermal bath mean for the future of any material trying to form planets there? The galaxy's brilliant light tells only part of the story. If you could see the cartwheel through a radio telescope tuned to the faint whisper of neutral hydrogen gas, its perfect ring would suddenly seem broken and incomplete. This primordial hydrogen, the raw fuel for star formation, is scattered in a bizarre and lopsided halo that stretches far beyond the visible starlight. It does not neatly trace the ring of fire, instead it forms a great asymmetric cloud enveloping the entire galaxy, with vast concentrations pooled on one side and startling voids on the other. This is the ghostly residue of the collision, a distribution of gas that defies the beautiful symmetry we see in visible light. Neutral hydrogen is the universe's basic building block, cold gas that has not yet been heated or ionized by starlight. During the colossal impact, this gas was not simply pushed outward in a neat circle. It was likely sent spinning and sloshing like water in a bucket that has been struck from an angle. The gravitational forces from the intruder galaxy, combined with the cartwheel's own frantic rotation, would have sent immense waves of this gas sloshing around the disk, some of it flung far out into the halo, some of it dragged along in the wake of the escaping intruder. The result is a chaotic, unsettled sea of potential that has not yet settled into the galaxy's new, ordered form. Why does the visible galaxy appear so symmetrical when its primary fuel source is in such a state of disarray? It suggests the star-forming ring is just a temporary pattern on the surface of a much deeper and more turbulent reservoir, a brilliant skin on a body that is still reeling from a primordial shock. How long will it take for this lopsided gas to settle, and will it eventually fall back inward to feed the ring or simply drift away, leaving the galaxy starved for fuel in the distant future? Its perfect form makes it a cosmic oddity. Ring galaxies like the Cartwheel are among the rarest structures in the entire observable universe. For every one of these celestial bullseyes, there are thousands upon thousands of ordinary spirals and ellipticals. This profound scarcity transforms the Cartwheel from a mere spectacle into a precious scientific laboratory. Its very existence provides a unique window into the most violent and transformative events a galaxy can experience. Why are these rings so uncommon? The conditions for their creation are incredibly specific. It requires a smaller galaxy to punch almost directly through the center of a larger, gas-rich disk galaxy. The angle, the speed, and the size of the intruder all have to be just right. A glancing blow might only warp the spiral arms, creating a messy, distorted galaxy. A head-on collision between two giants might simply merge them into a formless elliptical blob. The Cartwheel represents that perfect, improbable shot, a cosmic strike that sent a clean ripple through the galactic disk instead of just shattering it. Think of it like a stone skipping across a pond. Most throws will just make a splash or sink immediately, but on a very rare occasion with the perfect angle and spin, the stone will skip, creating a series of beautiful, expanding, circular ripples. The Cartwheel Galaxy is that one perfect skip on a universal scale. Its rarity is what makes it so invaluable. By studying its singular structure, we are not just learning about one galaxy, we are decoding the physics of galactic violence itself, understanding a process so fleeting and precise that it has left only a handful of examples across the vast cosmic sea. What other secrets of cosmic destruction and rebirth are locked within this one magnificent ring? Deep within the galaxy's ghostly core, a sleeping giant may have been violently awakened. The same collision that forged the brilliant outer ring could have sent a tsunami of gas rushing directly toward the Cartwheel's central supermassive black hole. In the chaotic aftermath of the impact, vast rivers of cold gas, ripped from their stable orbits, would have been funneled inward by the very same gravitational forces that scattered the core's stars. This would have created a sudden, colossal feast for the dormant black hole. When a supermassive black hole at a galaxy's center begins to consume matter at an incredible rate, the infalling gas heats up to millions of degrees, glowing with a brilliance that can outshine every star in the galaxy combined. This is a quasar, the most luminous and violent type of object in the entire universe. For a brief, spectacular period, the Cartwheel Galaxy might have blazed with this single, terrifying point of light at its heart, a beacon visible across the cosmos. So why do we see no such quasar today? The answer may lie in the very nature of the chaos that created it. The influx of gas was likely a short-lived storm, not a steady river. The black hole would have gorged itself in a frenzied burst of activity, shining with the power of a quasar for a few million years before consuming all the readily available fuel within its immediate grasp. Once that initial banquet was over, with no stable, ongoing supply of gas to sustain it, the engine would have sputtered and faded, leaving the black hole to return to its quiet slumber. The galaxy's ghostly core is the quiet after the storm, the evidence of a feast that has long since ended. It forces us to wonder, did we just miss the most spectacular show in the Cartwheel's history by a mere cosmic blink of an eye? The beautiful ring we see today is built upon the ruins of an older galaxy. Before the Great Collision, the Cartwheel was likely a majestic spiral, its disk filled with billions of stars living out their lives in quiet, orderly orbits. But what became of those original suns when the smaller galaxy tore through their home? Their fate is one of cosmic displacement, a scattering of the old to make way for the new. The immense gravitational shockwave from the impact did not discriminate. It acted like a colossal, invisible hand, reaching into the galactic disk and giving a tremendous push to countless stars. Many were violently flung outward, ejected from their familiar paths and sent on trajectories that carried them far beyond the bright ring. These exiled stars now form a vast, faint halo, a ghostly population that envelops the entire luminous structure. Picture a grand, ornate clock. The collision did not just shatter its face, it sent the individual gears and springs flying out in all directions, leaving them to drift in the darkness around the broken timepiece. These ancient stars are the galaxy's original citizens, now rendered homeless, orbiting in a diffuse cloud that testifies to the violence of their eviction. They are a permanent reminder of the spiral galaxy that once was, a galactic fossil record written not in stone, but in the faint, cold light of scattered suns. How many of these stellar refugees are drifting in the darkness, outshone by the brilliant new generations that replaced them? This bullseye perfection is a cosmic lie, a beautiful illusion born from pure chaos. The near-perfect circularity of the Cartwheel's main ring stands as one of its most baffling features. How could a random, violent collision, a glancing blow from an intruder galaxy, result in such a flawless geometric form? The answer lies in the precise physics of the impact itself. For a ring this symmetrical to form, the smaller galaxy had to strike the larger disk not with a direct hit, but at a very specific angle, one that sent a clean, expanding density wave through the gas-rich disk. Think of it like a hammer striking a vast, still gong. If you hit the gong's edge at a sharp angle, you get a messy, discordant clang. But if you strike its center dead on with the perfect force, you produce a pure, resonant tone that vibrates outward in a perfect circle. The creation of the Cartwheel was that perfect, resonant strike on a galactic scale. The initial chaos was immense, but the resulting shockwave self-organized, smoothing out its own imperfections as it traveled outward, compressing the gas into this stunningly uniform ring. It is the universe finding order in the aftermath of its own violence, a temporary equilibrium carved from a cataclysm. This perfect shape forces us to ask a deeper question about the nature of destruction itself. Can chaos under the right conditions be a sculptor of perfect forms? The brilliant chaos of the Cartwheel's visible matter is being orchestrated by an invisible hand. The way the stars and gas in that vast ring move, their speeds and trajectories simply do not make sense if you only account for the gravity of the glowing material we can see. There must be something else there, a tremendous amount of mass that emits no light, exerting a powerful gravitational pull on the entire system. This is the hidden role of dark matter, and the collision provided a unique opportunity to map its ghostly presence. When the smaller galaxy tore through the cartwheel, it did not just disturb the stars and gas. It also shook the galaxy's immense halo of dark matter, that mysterious, invisible substance that forms the gravitational backbone of every galaxy. By meticulously studying how the visible ring and core are moving in the aftermath, astronomers can work backward like detectives solving a case by observing how dust is disturbed in a room. The peculiar motions of the stars, the specific speed of the ring's rotation, and even the way the gas is sloshing in its lopsided halo all act as clues. These movements reveal the underlying gravitational landscape, a topography shaped not by light, but by the immense, unseen mass of dark matter. It is as if we are watching a flock of birds swirling in a stormy sky. We cannot see the wind itself, but by observing the precise paths the birds take, we can map every current and eddy of the invisible air. The collision gave us that storm, a violent event that set the visible galaxy in motion, allowing us to chart the contours of the dark matter halo that holds the entire structure together. Without this dominant, unseen mass providing extra gravity, the entire ring would have flown apart long ago, its stars scattered into the void. What does the specific shape of this dark matter halo tell us about the nature of the substance that makes up most of the galaxy's mass, yet remains forever hidden from our sight? This relentless ring of fire is also a factory of cosmic death. The Cartwheel Galaxy produces supernova at a staggering rate, far beyond what occurs in a typical, quiet galaxy like our own. A supernova is the final, catastrophic explosion of a massive star, a detonation so powerful it can briefly outshine its entire host galaxy. In the Milky Way, we might witness such an event only a few times a century. But within the Cartwheel starburst ring, these stellar cataclysms are a near-constant occurrence. This is the inevitable result of the collision's star-forming frenzy. The same shockwave that forged millions of new stars created a disproportionate number of stellar giants, stars that are many times more massive than our Sun. These colossal suns burn through their nuclear fuel in a cosmic sprint, living for only a few million years before their cores collapse and they detonate in a final, spectacular blaze. The ring is a supernova assembly line where stars are born massive and die young in a continuous, brilliant flash of self-destruction. How does it feel to witness a place where stellar death is not a rare tragedy, but a regular industrial process? Each of these explosions is a forge of creation, scattering newly forged heavy elements like iron, gold, and uranium deep into the surrounding gas clouds. This constant enrichment seeds the next generation of stars and any potential planets with the very elements that make rocky worlds and life itself possible. The Cartwheel's ring is not just a birthplace, it is a galactic recycler, using stellar death to build the foundations for a more complex future. What will this galaxy look like in a billion years after this storm of supernova has permanently altered its chemical destiny? That brilliant ring of fire is a temporary spectacle, a fleeting moment in the galaxy's multi-billion-year life. Current models of its evolution paint a strange and almost melancholic picture of its future. The very forces that created its stunning beauty are the same ones that will inevitably lead to its demise. The propagating starburst ring is like a wildfire consuming a finite forest. It is blazing through the galaxy's reserves of cold, dense gas at an astonishing rate, the very fuel required to form new stars. In a few 100 million years, perhaps as little as 400 million, this fuel will be exhausted. The great wave of star formation will simply have nothing left to burn. The ring's brilliant blue giants, the stars that give it its distinctive glow, are the first to die, exploding as supernova after only brief lives. Without new stars to replace them, the ring will gradually fade, its blue light dimming and reddening as only longer-lived, smaller stars remain. The galaxy will not vanish, but its defining feature, that perfect cosmic bullseye, will slowly dissolve into a much more diffuse and disorganized glow. What will be left when the fire goes out? The galaxy will likely settle into a far more common, yet still peculiar, shape. It may become a lenticular galaxy, a smooth, lens-shaped disk devoid of spiral arms, or even a featureless elliptical galaxy. Its history of violent rebirth will be hidden, visible only to astronomers who can read the subtle clues in the motions of its ancient stars. The Cartwheel's magnificent present is a short, brilliant chapter in a much longer story. A story that ends with the galaxy becoming something quiet, ordinary, and utterly transformed from the spectacle we see today. This cosmic collision was not a solitary event, but merely the loudest note in a continuous symphony of gravitational interaction. The Cartwheel Galaxy is not drifting in isolation. It is the largest member of a small, intimate group of galaxies, all bound together by their mutual gravity in a slow, cosmic dance. This galactic family continues to pull and tug at the cartwheel, their subtle but persistent forces adding new layers of complexity to its already strange story. While the initial impact created the ring, these neighboring galaxies are now the conductors, guiding the long-term evolution of its structure. Think of it as a planet with multiple moons, each one exerting its own tidal force, constantly reshaping the world's surface in small but cumulative ways. One of these companion galaxies, often identified as G3, shows clear signs of this intimate relationship. Long, faint bridges of hydrogen gas and even stars can be traced between it and the cartwheel, like celestial umbilical cords still connecting parent and child. These are not the violent scars of a single impact, but the gentle, ongoing strands of a gravitational bond that has persisted for billions of years. The intruder that caused the initial ring may be gone, but the cartwheel's dance card remains full. Its neighbors continue to exert their influence, subtly stirring the galaxy's lopsided gas halo and potentially influencing the future path of the star-forming shockwave itself. How many of these faint stellar streams connect the galaxies in this group, and what new patterns will their endless dance create over the next billion years? The cartwheel's stunning structure might be even more complex than it first appears. Astronomers have detected faint, arching streams of material that seem to rise above and below the galaxy's main disk, tracing a path that is almost perpendicular to the ring. This is the tantalizing hint of a polar ring, a structure that would make the galaxy doubly strange. A polar ring galaxy is one where a separate, distinct ring of stars, gas, and dust orbits around the galaxy's poles, the points directly above and below its central bulge. Imagine a planet like Saturn with its famous rings, but then picture a second, larger set of rings standing on edge, encircling the planet from north to south pole. That is the kind of bizarre, cross-shaped configuration we might be seeing the beginnings of in the cartwheel. How could such a thing form? The most likely culprit is once again the ancient collision. When the smaller galaxy was torn apart during its plunge, not all of its debris was flung outward in the main plane of the cartwheel. Some of it could have been sent into a highly inclined orbit, a vast cloud of gas and stolen stars that began to loop over the galaxy's poles. Over time, as this material circles the cartwheel, its own gravity could cause it to collapse into a thin, bright ring, a secondary structure that wraps around the primary one at a right angle. We are not seeing a fully formed polar ring yet, but rather the ghostly scaffolding from which one could be built. This suggests the collision's aftermath is still settling into its final, stable form, and that the cartwheel's transformation is not yet complete. What would it mean for a galaxy to possess two distinct rings, one in its waist and one over its head? And what secrets about the original intruder's trajectory are written in that perpendicular arc? A strange silence echoes across millions of years within the Cartwheel stellar population. When astronomers listen to the galaxy's history by analyzing the ages of its stars, they encounter a profound gap, a missing generation that should tell the story of the collision's immediate aftermath. This is the mystery of the absent intermediate age stars. We see the ancient original stars that were scattered during the impact, and we see the brilliant newborn stars lighting up the current ring. But the stars that should have formed in the turbulent millions of years between these two eras are conspicuously faint and few in number. It is as if the galaxy's star-forming machinery shut down completely for a significant period after the initial catastrophe, only to roar back to life with the starburst ring we see today. This population gap is a crucial clue, a cosmic timer that helps us sequence the collision's chaotic events. The most likely explanation is one of sheer exhaustion. The initial collision may have triggered a frantic, short-lived burst of star formation that rapidly consumed all the easily available gas in the inner regions. This first wave of creation would have left behind a galaxy temporarily starved of fuel, a barren landscape where no new stars could form for tens of millions of years. Then, as the shockwave from that initial impact continued its slow, relentless journey outward, it finally reached the galaxy's pristine, untouched outer reservoirs of gas. Only then, when this propagating wave began to compress these vast, virgin clouds, did star formation ignite again on a colossal scale, creating the ring and leaving this eerie quiet period sandwiched between two eras of furious activity. Why did the galaxy take so long to recover, and what does this tell us about the true, delayed power of a collision's gravitational ripple? That brilliant ring of fire is threaded with invisible lines of force. Woven through the searing gas and dust of the Cartwheel starburst ring are magnetic fields of incredible strength, cosmic filaments that have been amplified and organized by the very same violence that shaped the galaxy. These are not the weak, scattered magnetic fields of a quiet spiral like our Milky Way. Here they have been supercharged, becoming a powerful and dynamic component of the galactic machinery. Imagine the difference between the faint magnetic field around a simple bar magnet and the intense, focused field generated by a massive particle accelerator. The collision provided the energy for that amplification. As the colossal shockwave plowed through the galactic disk, it did not just compress gas, it also stretched and folded the galaxy's primordial magnetic fields, weaving them into a more coherent and vastly more powerful structure. This process is like braiding ropes, taking many weak, thin strands and twisting them together into a single, unbreakable cable. These amplified fields now act as cosmic guides, invisible rails that channel the flow of ionized gas and help control the chaotic process of star formation. They can provide support against gravity, preventing some clouds from collapsing too soon, while in other areas they might funnel material together, accelerating the birth of new stellar giants. This magnetic tapestry adds a hidden layer of order to the apparent chaos, a subtle architecture within the storm. How does this invisible web determine which gas clouds become stars and which are held back, and what role did these magnetic threads play in creating the ring's perfect, coherent shape? For all its ferocious activity, the Cartwheel Galaxy holds back some of its light. This is the curious problem of its luminosity, a puzzle where the brilliant ring of fire does not shine as brightly in visible light as our best models insist it should. With so many millions of new stars being forged, the galaxy ought to be an almost blinding beacon. Yet its optical glow is strangely muted, falling short of expectations. This discrepancy points to hidden factors operating within the chaotic ring. One of the prime suspects is an immense amount of cosmic dust. The same collision that triggered this starburst also churned up colossal clouds of fine, dark silicate and carbon grains. These tiny particles act like a galactic-scale fog, absorbing and scattering the visible light from the newborn stars before it can escape into space. The starlight is there, but it is being trapped, converted into the searing infrared heat we detect instead. Another possibility lies in the very nature of the stars being born. Our models often assume a standard mix, a predictable distribution of small, long-lived stars and massive, brilliant giants. But what if the Cartwheel's extreme conditions are producing a different kind of stellar population altogether? Perhaps it is favoring the formation of many more small, faint stars over the truly colossal blue giants, a skewed initial mass function that would create plenty of heat and long-term stability, but less of the immediate, dazzling optical brilliance we expect. It is like expecting a forest of towering sequoia trees and instead finding a vast woodland of dense, shorter pines. The total mass of wood might be the same, but the visual impact from a distance is profoundly different. This luminosity problem forces us to question our most basic assumptions about star formation under duress. Are we truly seeing the galaxy's full stellar output, or is most of its creation story hidden behind a veil of its own making? High-resolution observations of the Cartwheel reveal a subtle ghost in the machine. Nestled just inside the blazing main ring, astronomers have detected a fainter, secondary arc of starlight, a delicate echo of the primary structure. This is not a trick of the light, but a potential ring within a ring, a whisper of a more complex story than a single, simple collision. How could such a nested structure form? One compelling theory suggests this inner ring is the fossilized imprint of a second, weaker shockwave. Picture the initial impact like a hammer striking a gong, sending out the primary, world-shaping wave that created the brilliant outer ring. But as that wave expanded, it may have triggered a secondary reverberation, a smaller, reflected pulse of energy that traveled back inward through the galactic disk. This fainter echo would have compressed a different reservoir of gas, igniting a later, less intense wave of star formation that left this ghostly inner ring as its signature. Another, more dramatic possibility involves the very nature of the collision itself. Perhaps the intruder galaxy did not simply punch through and move on. Its trajectory might have been so complex that it delivered not one, but two distinct gravitational blows as it entered and then exited the Cartwheel's disk, creating two separate ripples in the galactic pond. The main ring would be the result of the first, most violent impact, while this fainter, inner ring could be the signature of the intruder's final, parting shot as it tore back out through the gas. This nested structure challenges the simple story of a single, clean collision, suggesting instead a drawn-out and far more chaotic encounter. It implies that the galaxy's rebirth was not a single event, but a sequence of cosmic tremors, each leaving its own distinct mark on the evolving galactic landscape. What other faint echoes are waiting to be found? And what would it mean if the Cartwheel's beautiful form was sculpted not by one strike but by several? Even the galaxy's heat signature carries a mystery of its own. When astronomers analyze the Cartwheel's intense infrared glow, they find that it is not a smooth, continuous spectrum. Superimposed on that thermal blanket are strange, broad bumps and ridges of light, specific wavelengths where the galaxy emits an unexpected surplus of energy. These are the unidentified infrared bands, spectral fingerprints that do not match the signature of any known atom or simple molecule. It is as if you were listening to a symphony and hearing a recurring, beautiful chord played by an instrument you cannot identify. The most compelling theory points to vast clouds of complex carbon-based compounds known as polycyclic aromatic hydrocarbons. Imagine microscopic flecks of soot, not as simple as the carbon in charcoal, but structured into intricate, honeycomb-like lattices, similar to fragments of graphene or tiny, frozen snowflakes made of carbon and hydrogen. These molecules, when warmed by starlight, vibrate and twist in specific ways, emitting light at these very distinct infrared frequencies. Their possible presence here is a profound puzzle. The Cartwheel's ring is a maelstrom of destructive ultraviolet radiation and violent supernova shocks, an environment that should tear such complex organic molecules apart almost instantly. How can something so seemingly delicate survive in a celestial forge of such fury? Their endurance suggests they are either being continuously manufactured in vast quantities, or they are finding shelter within dense, cold clouds that shield them from the galaxy's relentless energy. These unidentified bands are more than just a spectral curiosity. They are a potential signpost for the fundamental building blocks of chemistry, thriving against all odds within a galaxy that should be tearing them to pieces. What does it mean for the raw ingredients of complexity to not only exist, but to possibly flourish in the most violent and inhospitable place we can imagine? This cosmic engine may be firing invisible bullets into the void. The same violent processes that light up the Cartwheel Galaxy in visible and X-ray light could also be transforming it into a powerful source of gamma rays, the most energetic form of light in the entire universe. These are not mere photons, they are cosmic projectiles, each one carrying millions of times more energy than a particle of visible light. To produce gamma rays, you need nature's most powerful particle accelerators, and the Cartwheel is practically a factory for them. The prime suspects are the same ultraluminous X-ray sources and the relentless supernova remnants we have already met. Picture a supernova shockwave expanding at thousands of kilometers per second, plowing into the surrounding gas and dust like a colossal, supersonic bulldozer. This creates a turbulent frontier where subatomic particles can become trapped, bouncing back and forth across the shock front and gaining tremendous speed. These particles, often protons or electrons, are accelerated to nearly the speed of light. When they finally collide with other particles or even photons of starlight, the impact is so violent it forges a gamma ray. The galaxy's abundant ULXS offer another pathway. The intense magnetic fields around a feeding black hole can act like a synchrotron, whipping charged particles to incredible energies before flinging them out into space, where they too can collide and produce this searing radiation. The Cartwheel, with its dense concentrations of these extreme objects, could be shimmering with a high-energy glow that our eyes cannot see. This potential makes the galaxy a prime target for space telescopes like the Fermi Gamma Ray Space Telescope, which scans the heavens for these faint, high-energy signatures. Detecting a distinct gamma-ray signal from the Cartwheel would be like finding the invisible exhaust from its most powerful engines, confirming that this beautiful ring is not just a birthplace for stars, but also a cosmic powerhouse for the universe's most extreme radiation. What other secrets of particle acceleration are being written in this invisible light? And what would it mean if this single galaxy was a significant source of energy for the entire cosmos? A rainbow of cosmic history is painted across the Cartwheel's face. Its brilliant outer ring shimmers with the searing blue-white light of newborn stellar giants, while the faint central hub glows with the deep, ruddy hue of ancient, cooling suns. This is the galaxy's color gradient, a visual timeline that should, in theory, tell a simple story of violent rebirth at the edges and quiet old age at the center. Yet the transition between these two extremes is far from smooth. The gradient is not a perfect, gradual wash from blue to red, but is instead broken and mottled, marked by patches of unexpected color and strange, intermediate hues that defy a simple narrative. Why isn't this cosmic painting as clean as our models predict? The answer lies in the messy, stop-and-start nature of the galaxy's star formation history. The collision did not simply turn on a single, galaxy-wide switch for creating stars. Instead, it was a chaotic, multi-phase process. The initial impact likely triggered a frantic burst of star formation that was concentrated in the inner regions, a first wave of creation that was later choked off as it exhausted its local fuel supply. This first generation of stars has since aged, leaving behind a redder population that is now intermixed with the truly ancient stars of the original core. Then, millions of years later, the propagating shockwave reached the pristine outer gas, igniting the brilliant blue ring we see today. The result is a layered and lumpy color map, a celestial canvas where different eras of stellar birth are superimposed on one another. It is like looking at a forest that has burned multiple times, where you can still see the charred remains of the oldest trees, the mature growth from a later fire, and the vibrant new saplings sprouting from the most recent blaze, all existing side by side. This broken gradient is the true story of the Cartwheel, a testament not to a single event but to a long and turbulent recovery, a galaxy that has been remade in fits and starts, its full history written in a disrupted spectrum of light. What other stories of delayed creation and sudden, violent renewal are hidden within these subtle shifts in color? This expanding ring of fire behaves like a cosmic memory, a slow-motion replay of the initial catastrophe. A similar principle can be found in the ghostly aftermath of a supernova, where we observe a phenomenon known as a light echo. When a massive star explodes, its final flash of light illuminates vast, distant shells of dust that were previously invisible. The light from the explosion reaches us first, but then, years or even decades later, we see that same light again, reflected off dust clouds that are slightly farther away. It is the same event, the same burst of energy, but its signature is stretched across time, creating multiple apparitions of a single moment. The Cartwheel Galaxy's starburst ring is a kind of stellar evolution echo, a vastly amplified and prolonged version of this same idea. The initial collision was the flash, the single, violent moment of the intruder's impact. The expanding ring is not a reflection of light, but a physical wave of consequence, a ripple of gravitational energy that triggers star formation as it travels. Just as a light echo allows us to study a supernova long after its light has faded, this stellar echo lets us witness the collision's transformative power millions of years after the event itself. The galaxy is literally acting out its own history, using the birth of new stars to trace the path of an ancient shockwave. It is a fossil record written not in stone, but in the ongoing, brilliant process of creation itself. What other cosmic echoes are we missing, simply because they unfold over timescales too vast for us to easily perceive? Within that brilliant ring, the gas is engaged in a ceaseless, supersonic war with itself. This is not a calm, swirling nebula, but a maelstrom of pure turbulence, where vast clouds of hydrogen and dust crash into one another at speeds far exceeding that of sound. Imagine the chaos of a hurricane, but on a scale so immense it could swallow entire solar systems, with wind speeds measured in thousands of kilometers per second. This incredible violence creates a strange and delicate balance, a self-regulating cycle that both gives birth to stars and strangles them in their cribs. On one hand, turbulence is the great trigger. When these supersonic gas clouds collide, they create pockets of extreme density, regions of such intense pressure that gravity can finally take over and pull the gas inward to collapse into a new star. It is the cosmic equivalent of shaking a box of scattered Lego bricks, causing them to randomly bump into one another and occasionally snap together into a larger structure. Yet, on the other hand, this same turbulence is a powerful stabilizer. The chaotic, supersonic motions generate immense kinetic energy within the gas clouds themselves. This internal energy acts like a powerful support structure, a form of pressure that pushes back against the relentless pull of gravity. A cloud may begin to collapse under its own weight, but the wild, churning motions within it can keep it puffed up and stable, preventing it from fragmenting into stars. So the ring exists in a perpetual state of push and pull, where turbulence simultaneously builds up the dense knots that become stars, while also providing the violent support that prevents most of the gas from ever collapsing. It is a cosmic engine that fuels its own fire while carefully controlling the flame, ensuring the starburst does not consume all its fuel in a single, catastrophic burst. How does this chaotic system find any equilibrium at all, and what would happen if this turbulent balance were to suddenly tip? Even the galaxy's distance from us is a subject of cosmic debate. For decades, astronomers have struggled to pin down the exact mileage to the cartwheel, and this is not a trivial accounting error. The precise number, whether it is 400 million light-years or perhaps 500 million, fundamentally changes our understanding of everything about it. If we get the distance wrong, we miscalculate its true size, the sheer physical scale of that magnificent ring, and the intrinsic brightness of every star and supernova within it. The challenge lies in the methods themselves. One common technique involves identifying a special class of pulsating stars known as Cepheids variables within the galaxy. These stars brighten and dim with a clockwork regularity that is directly tied to their true luminosity. By measuring their pulse and their apparent brightness from Earth, we can calculate their distance with remarkable precision. Yet applying this to the cartwheel is fraught with difficulty. Its core is too faint and puffed up, and its brilliant ring is too crowded and dust-choked, making it incredibly hard to pick out individual Cepheid stars from the brilliant chaos. Another method uses the light of entire supernova, treating them as standard candles, but these colossal explosions are fleeting events, and catching one at the right moment in the cartwheel is a matter of luck. Each technique, with its own subtle assumptions and potential for error, has delivered a slightly different answer. It is like two expert surveyors using different tools to measure the same mountain, one reporting its height as 8,000 feet and the other insisting it is 8,500. Both are skilled, both are scientific, but the gap between their results leaves the true grandeur of the mountain in question. This ongoing debate reminds us that even the most stunning cosmic certainties are built upon a foundation of meticulous and sometimes contentious measurement. What other secrets about the cartwheel's nature are hiding within that unresolved gap of 100 million light-years? A galaxy's chemistry often reads like a history book, with the oldest, most metal-poor stars clustered in the halo and the youngest, metal-rich generations lighting up the core. This is the classic metallicity gradient, a predictable decline in heavy elements as you move from the bustling galactic center out to the quiet suburbs. The Cartwheel Galaxy, however, has torn that textbook to shreds. Its violent history has effectively taken a cosmic blender to its chemical composition, scrambling any orderly pattern into a strange and disorganized mess. The result is a puzzlingly homogeneous mix, or perhaps even an inverted gradient, where the outer ring might be just as rich in heavy elements as the faint central hub. How does a galaxy lose its chemical fingerprint? The answer lies in the sheer violence of the collision. The immense gravitational shockwave did not just trigger star formation, it acted like a colossal stirrer, churning the galaxy's gas on an unimaginable scale. Before the impact, the cartwheel likely had a normal gradient, with its core enriched by eons of stellar evolution. But when the intruder galaxy struck, it sent vast waves of gas sloshing from the center out to the edges and back again. This cosmic mixing bowl flung metal-rich gas from the inner regions out into the ring, while simultaneously pulling pristine, metal-poor gas from the outer disk inward toward the core. The propagating starburst ring itself then compounded this effect, acting as a giant, self-contained recycling plant. As we've seen, it forms massive stars that quickly die as supernova, blasting newly forged metals back into the surrounding gas. This constant, furious enrichment in the ring keeps its metallicity artificially high, while the churned up and scattered core never had a chance to re-establish a dense, metal-rich heart. Imagine a city where a catastrophic event forces everyone to evacuate, scattering the wealthy elite and the impoverished equally across the entire metropolitan area, erasing all the old neighborhoods and their distinct identities. The Cartwheel is that city on a galactic scale, its chemical map rendered nearly uniform by a single, world-shattering event. What does this chemical chaos tell us about the true power of a collision to not just reshape a galaxy's structure, but to rewrite its very elemental identity? Deep within the galaxy's pale heart, a population of ancient survivors may be hiding. The ghostly core of the Cartwheel Galaxy could be concealing what astronomers call red nuggets, the dense, fossilized remains of some of the universe's first galaxies. These are not individual stars, but entire galactic cores in their own right, compact cities of ancient, red stars that formed billions of years ago. They are thought to be the primordial building blocks from which giant galaxies like the Cartwheel were originally assembled. The great collision that reshaped this galaxy would have been a perfect opportunity to capture these cosmic fossils. As the smaller intruder galaxy was torn apart during its plunge, it likely did not travel alone. It would have been surrounded by its own entourage of tiny, dwarf satellite galaxies. The Cartwheel's immense gravity would have easily ensnared these smaller companions, dragging them down into its newly churned core. Unable to withstand the tidal forces, these dwarf galaxies would have been stripped of their outer stars, leaving only their incredibly dense, resilient cores intact. Imagine a massive whirlpool in a cosmic ocean, not just stirring the water, but pulling in smaller, sturdy boats and breaking them apart, leaving only their heavy, indestructible metal engines to sink to the bottom. Those engines are the red nuggets sinking into the diffuse heart of the Cartwheel. They would now orbit the central supermassive black hole, their vast age and red glow camouflaged by the pale light of the other scattered stars. This would mean the galaxy's core is not just a scattered population of its own original stars, but a cosmic graveyard filled with the immortal hearts of galaxies it consumed long ago. How many of these ancient galactic seeds are hidden there, and what stories of the early universe are locked within their silent red suns? Those dark, crooked spokes are not static scars. They are rivers in motion, flowing with currents of gas and stars that defy simple explanation. Spectroscopic data allows us to measure the velocity of this material, and the results are chaotic. The motion is not a clean, radial flow straight in toward the core or out toward the ring. Instead, we see complex, turbulent kinematics with gas streams twisting, colliding, and even flowing in directions perpendicular to the main structure. This suggests the spokes are not stable, permanent features. They are dynamic, evolving structures riddled with instabilities that are still working themselves out millions of years after the collision. Picture a long, narrow cloud of smoke, but instead of drifting smoothly in one direction, it is churning and folding back on itself, with different parts moving at different speeds and in different ways. The gravitational pull from the galaxy's lopsided core and the intense radiation pressure from the ring are constantly tugging at these dusty rivers, stirring them into a frenzy. This ongoing dynamical evolution means the spokes are temporary. They are not the galaxy's final form, but rather a transitional phase, a snapshot of a system still settling from its violent rebirth. The strange kinematics tell us that the Cartwheel's beautiful skeleton is still shifting, its bones not yet set as it continues to heal from the ancient wound that created it. This beautiful wreckage is a window into the universe's violent youth. The Cartwheel Galaxy offers us more than a spectacle. It is a functioning time machine, a rare glimpse of a phase most galaxies experienced billions of years ago. In the early cosmos, the universe was a much denser, more chaotic place. Galaxies were closer together, and colossal collisions like the one that forged the Cartwheel were commonplace. These violent encounters were the primary engines of galactic change, triggering immense bursts of star formation, building up central black holes and scrambling the chemical composition of entire systems. For nearly every massive galaxy we see today, including our own Milky Way, this chaotic period of bombardment and merger is a foundational chapter in its deep history. But that era is largely over. The universe has expanded, stretching galaxies apart and making such direct, transformative impacts incredibly rare events in the modern cosmic calendar. The cartwheel is a precious relic, a living fossil from that bygone age of fire. It is as if we have discovered a single, thriving dinosaur, a creature from a lost world that somehow survived into the present day, allowing us to study its biology directly instead of piecing it together from bones. We are witnessing a process that built the universe but which has now mostly ceased. What fundamental rules of galactic construction are written in the cartwheel's brilliant ring? Rules that shaped everything we see around us, but which we can no longer observe in action anywhere else. A faint, persistent crackle underlies the ring's brilliant light. Peppered throughout the cartwheel's fiery circumference are countless compact radio sources, points of intense energy that hum a silent song our eyes can never see. These are not the gentle radio whispers of a quiet galaxy, but the sharp, distinct signatures of extreme violence confined to tiny, unresolved points. Each one is a mystery, a tiny radio beacon whose true nature is blurred by the sheer distance and the crowded, chaotic environment of the ring itself. They are likely a mix of two powerful cosmic phenomena, both born from the relentless starburst. Some are the expanding shells of recent supernova remnants, the colossal shockwaves from stellar explosions plowing through the surrounding gas at supersonic speeds. This violent motion generates a fierce radio glow, a temporary tombstone marking the death of a massive star. Other sources could be the furious winds from the most massive stars still shining. These stellar giants do not burn gently, they rage, expelling their own outer layers in a continuous supersonic gale. When these powerful winds slam into the slower-moving gas around them, the collision creates a turbulent shock front that also blazes in radio waves. The problem is that from our vantage point, hundreds of millions of light-years away, these different types of objects, the dead stars and the living ones, blur together into a single, unresolved point of radio light. We know the energy is there, we can hear its distinct signature, but we cannot always tell if we are listening to the birth cry of a stellar wind or the death rattle of a supernova. It is like standing outside a bustling, illuminated city at night. You can see the individual lights of countless windows, but from a distance, you cannot tell which light comes from a quiet office, which from a raging factory, and which from a single, burning building. This unresolved radio chorus is the sound of the ring's inner turmoil, a cacophony of creation and destruction whose individual instruments we are only just beginning to distinguish. What new kinds of stellar violence might be hiding within that static, waiting for a powerful enough telescope to finally bring them into focus? This brilliant ring of fire is its own worst enemy. The very stars it creates hold the power to strangle their own successors in a strange, self-regulating cycle of cosmic feedback. This is not a simple process of birth and death, but a continuous loop of creation and suppression. Each massive newborn star is a furious engine, and it does not burn quietly. It unleashes a relentless gale of charged particles, a supersonic stellar wind that streams outward in all directions, pushing against the surrounding gas like an invisible hand. When these stars reach the end of their brief lives, they do not fade away, they detonate. A supernova explosion is the ultimate expression of this feedback, a blast wave of unimaginable force that slams into the galactic environment. This is where the cycle turns back on itself. All that injected energy from the winds and the supernova heats the surrounding gas clouds to extreme temperatures and churns them into a state of violent turbulence. Think of a pot of water on a stove. A gentle simmer might allow small bubbles to form and merge, but if you turn the heat to its maximum, the water erupts into a furious, rolling boil where no stable bubbles can form at all. The feedback from the stars is that intense heat. It prevents the cold, dense clumps of gas from peacefully coalescing under their own gravity. It effectively blows the raw material for new stars apart, shutting down star formation in that immediate area. Yet, paradoxically, this is not the end of the story. As those powerful shockwaves travel outward, they can eventually encounter quieter, more distant reservoirs of gas. When a supernova blast wave plows into one of these pristine clouds, it does not just heat it, it violently compresses it. The shock front acts like a cosmic snowplow, gathering a huge wall of gas and dust and pushing it into an incredibly dense shell. And within that compressed shell, the conditions can become just right for a new, delayed wave of star formation to ignite. So the same force that suppresses creation in one location can be the very trigger for it in another. The galaxy's starburst is not an unchecked fire, it is a carefully controlled burn, a cycle of furious activity that contains the seeds of its own limitation, ensuring the ring does not consume its entire fuel supply in a single, fleeting burst of glory. How many potential stellar nurseries are being held in check by this invisible pressure, waiting for a distant shockwave to finally set them free? Its immense mass could warp the very fabric of space around it, acting as a colossal lens. This is the Cartwheel's potential for gravitational lensing, a strange and subtle phenomenon where the galaxy's gravity bends the light from objects far behind it. According to Einstein's theory of general relativity, a massive object like a galaxy does not just sit in space, it creates a dip in the cosmic fabric, a gravitational well. When light from a distant galaxy travels through this warped region on its way to our telescopes, its path is curved, just like light passing through a giant cosmic magnifying glass. The effect can be spectacular, stretching the background galaxy's image into long, faint arcs or even creating multiple mirrored images of the same object. For the Cartwheel to produce this effect, its total mass, including the immense halo of dark matter we know surrounds it, must be perfectly aligned with an even more distant galaxy from our point of view. The challenge is that the Cartwheel itself is so brilliant and complex, its own dazzling ring of fire could easily drown out the faint, distorted ghost of a galaxy billions of light years further away. Detecting such a lensed image would be like trying to spot the reflection of a candle in a windowpane while staring directly into the sun. Yet if astronomers could confirm this, it would be a profound discovery. It would give us an independent way to weigh the Cartwheel's total mass, dark matter and all, by measuring how strongly it bends the light. It would also grant us a clearer view into the ancient universe, using the galaxy's own gravity as a natural telescope to peer at galaxies too faint and distant for our instruments to see on their own. Is the Cartwheel currently magnifying some primordial galaxy from the cosmic dawn, its light bent and twisted into a faint, beautiful arc that we have simply not yet learned to see? The Cartwheel is not the universe's only perfect ring. Far across the cosmos floats another celestial bullseye known as Hoag's object, a galaxy so symmetrically beautiful it seems almost artificial. Yet placing these two stunning rings side by side reveals a profound cosmic mystery. Hoag's object presents a nearly flawless circle of young blue stars surrounding a calm, ancient yellow core with a clean, dark gap of empty space between them. There are no crooked dust spokes, no lopsided gas halos, and no smaller companion galaxies nearby that could be blamed for a recent hit and run. Its origin remains one of astronomy's greatest puzzles, with theories ranging from an extremely ancient, forgotten collision to a bizarre and rare form of stable galactic structure we simply do not yet understand. The Cartwheel, by stark contrast, is a crime scene with the evidence still scattered everywhere. Its ring is a place of violent, ongoing creation. Its core is a scattered ghost, and its entire being shouts the story of a recent colossal impact. This comparison elevates the Cartwheel from a mere spectacle to a confirmed case study. It is the definitive example of an impact ring galaxy, a living laboratory where we can observe the physics of galactic collisions in furious, real-time action. Hoag's object is the serene, unreadable Sphinx, while the Cartwheel is the open book, its pages torn and stained, but its story screaming from every chapter. Why does the universe create two such similar forms through what appear to be entirely different means? One is a portrait of cosmic peace, the other a snapshot of celestial violence, and both are telling us that the path to a perfect ring is far stranger than we ever imagined. Any pre-existing worlds in this galaxy faced a cosmic apocalypse beyond comprehension. The collision would have been an absolute end for countless solar systems, a final chapter written in gravitational fury and searing radiation. Planetary orbits, once stable for billions of years, were suddenly transformed into chaotic, unstable pathways. Some planets were likely flung from their stars entirely, ejected into the blackness of intergalactic space to become permanent orphans, frozen dark worlds on an endless solitary journey. Others faced a more violent end, their orbits perturbed until they plunged directly into their host stars or collided with sibling planets in a final, fiery cataclysm. For those worlds that somehow clung to their orbits, the aftermath offered no reprieve. The ensuing starburst bathed the entire galaxy in that lethal radiation we discussed earlier, a continuous, sterilizing blast of ultraviolet and X-ray energy. Any atmosphere that survived the initial gravitational chaos would have been stripped away, any ocean boiled into vapor, and the very surface of any rocky world scoured clean. The concept of a habitable zone, that delicate orbital region where liquid water can exist, became utterly meaningless. The entire galaxy, for a time, was transformed into a single, unified sterilization chamber. This forces us to contemplate a profound and unsettling idea. If life had somehow taken root in the original spiral galaxy, it would have been utterly erased, its existence snuffed out on a galactic scale. The beautiful ring we admire today is built upon the ruins of countless potential worlds, a cosmic rebirth paid for with the absolute destruction of all that came before. What does it mean for a galaxy's creative potential to be so deeply intertwined with its capacity for absolute annihilation? The galaxy's brilliant blue ring might be painting a deceptive picture of its true cosmic health. On the grand chart astronomers used to classify galaxies, a diagram plotting color against brightness, the Cartwheel occupies a strange and precarious middle ground known as the Green Valley. This is not a literal color you would see with your eyes, but a spectral fingerprint of a galaxy caught between two states of being. On one side of this chart lie the blue cloud, galaxies that are actively and vigorously forming new stars, their light dominated by the searing blue glow of stellar nurseries. On the other side rests the red sequence, galaxies that have effectively died, their star formation ceased, leaving behind a population of old, cooling red stars. The Green Valley is the short, transitional highway between these two extremes, and the Cartwheel is speeding down it. Its vibrant blue ring screams of life, but that very activity is a feverish final burst. It is burning through its remaining fuel so quickly that it is essentially committing galactic suicide in a blaze of glory. This starburst is so intense and wasteful that it will inevitably lead to a premature aging of the entire system. Imagine a brilliant firework that uses all of its powder in one magnificent, concentrated explosion. For a few moments, it outshines every other light in the sky, but then it vanishes, leaving behind only a fading trail of smoke. The Cartwheel is that firework on a galactic scale. Its current spectacle is a sign of its impending transition into the red sequence, a future where its ring will fade and the galaxy will settle into a quiet, redder, and far more passive existence. How many other galaxies have taken this rapid, self-destructive path to retirement, and what does it mean for our own Milky Way, which is drifting far more slowly and peacefully through the blue cloud? The galaxy's furious star factory should be overflowing with fuel, yet it is strangely frugal. Deep within the beautiful chaos of the Cartwheel's ring, astronomers have made a puzzling discovery about its molecular gas. This is not the simple hydrogen that fills the galaxy's outer halo, but something far more complex and crucial. Molecular gas consists of hydrogen atoms that have paired up into molecules, often bound together with dust grains in cold, dense clouds. This specific, frosty form of matter is the universe's premium star-forming material. the only kind cold and dense enough to collapse under its own gravity and ignite new suns. In a starburst galaxy like the Cartwheel, you would expect to find colossal reservoirs of this gas, vast stockpiles ready to feed the inferno for eons to come. But the observations tell a different, more perplexing story. The molecular gas is there, but it is not as abundant as the staggering rate of star formation would suggest, and its distribution is oddly patchy. It is as if you discovered a massive steel mill operating at full capacity, its furnaces blazing day and night, yet its main storage yard for raw iron ore is only half full. How can the factory be so productive if it is not constantly receiving massive new shipments of fuel? This presents a fundamental puzzle of galactic economics, a question of income versus expenditure. The galaxy is clearly consuming its molecular gas at a breakneck pace to power the starburst ring, but the reserves we can detect do not seem sufficient to sustain this level of production for long. So where is the rest of the fuel? One possibility is that our observations are simply missing a hidden component. The molecular gas could be trapped in a form that is incredibly difficult for our telescopes to see, perhaps locked away in countless tiny, dense clouds that are camouflaged within the brilliant light and complex structure of the ring. Another, more dynamic explanation involves a delicate cycle of destruction and renewal. The same supernova and stellar winds that are born from the molecular gas are also constantly tearing it apart. The intense radiation from massive stars can blast through these cold clouds, breaking the delicate molecular bonds and heating the gas back up into a hot, atomic state where it cannot form stars. But then, in the turbulent wake of a supernova blast, this hot, dispersed gas might rapidly cool and recombine back into new molecular clouds, ready to collapse once more. The galaxy could be running a just-in-time delivery system, where gas is converted from atomic to molecular form, and then immediately consumed by star formation in a continuous, frantic loop. There is no vast warehouse, only a hyper-efficient assembly line that creates the fuel mere moments before it is thrown into the furnace. This leaves us with a critical question. Is the Cartwheel's magnificent ring the result of a final, glorious binge on a finite supply of gas, or is it a sustainable process, a cosmic engine that has found a way to recycle its own fuel with astonishing speed? The answer will determine whether we are witnessing a galaxy at the peak of its power or already beginning its long, slow fade into the red. Its true face is a collage of hidden portraits. To see the Cartwheel Galaxy as it really is, you must look with more than your eyes, viewing it through the different filters of the electromagnetic spectrum. Each wavelength of light it emits is a separate chapter in its violent story, revealing a different layer of its strange reality. In the familiar glow of visible light, we see the iconic blue ring of newborn stars, a perfect bullseye of cosmic creation. But this is the most superficial layer, the galaxy's public face. Switch your vision to the infrared, and the entire scene transforms. The brilliant ring is still there, but now it is engulfed in a furious, all-encompassing fire of its own making. This is the glow of superheated dust, fine grains of silicon and carbon, baked to millions of degrees by the intense radiation from all those young stars. The infrared reveals the sheer thermal violence of the starburst, showing that the entire structure is not just shining, it is simmering with a trapped, searing heat that our eyes can never perceive. Then peer into the high-energy realm of X-rays. Suddenly, the smooth ring fractures into a scattered constellation of brilliant, piercing points of light. Each one is an ultraluminous X-ray source, a cosmic predator like a black hole or neutron star in the act of devouring a companion. The X-ray vision strips away the galaxy's beautiful facade and shows you its monstrous heart, the dozens of hyperactive engines powering the chaos from within. Finally, tune your telescope to the long, quiet waves of radio light. The perfect ring of stars vanishes, replaced by a lopsided, messy halo of cold, neutral hydrogen gas. This is the galaxy's ghostly fuel tank, the raw material for future stars, and it is sloshing around in a chaotic, unsettled sea that defies the beautiful symmetry of the visible ring. This radio portrait reveals a system still reeling from the impact, its primary building blocks flung into a disorganized cloud that has not yet settled into the new order. So which of these portraits is the real Cartwheel? The answer is all of them. The galaxy is not one thing, but a composite of visible fury, invisible heat, hidden monsters, and unsettled potential. A single entity whose full story can only be read by listening to every note in its complex cosmic song. Even our most powerful supercomputers cannot perfectly recreate this cosmic bullseye. When astronomers feed all the known data into state-of-the-art simulations, programming the laws of physics to replay the Cartwheel's collision, the virtual result is always slightly off. The computers can produce a ring, but it might be too faint, or the crooked spokes might not form with the right twist, or the distribution of gas will look a little too neat. It is as if we have the right musical score, but our orchestra is missing a few crucial instruments, and the symphony never sounds quite right. This is the simulation challenge, a humbling reminder that our understanding of galactic violence is still incomplete. The models struggle to capture the full, messy complexity of real-world physics, particularly the role of magnetic fields and the intricate, turbulent feedback between stars and gas. We can simulate a shock wave, but can we simulate the exact way a supernova's blast ripples through a cloud, simultaneously tearing it apart and triggering new collapse? We can program gravity, but can we accurately model the way dark matter sloshed and settled during the impact? Every mismatch between the simulation and the real galaxy is a clue, a signpost pointing toward a piece of physics we have not yet fully accounted for. It suggests that in the extreme crucible of a galactic collision, matter and energy behave in ways we are only beginning to grasp. What fundamental rule of cosmic chaos are we still missing? A rule written plainly in the stars of the Cartwheel, but which our most advanced digital worlds have yet to learn. Its image has transcended the pages of astronomical journals to become a true icon of our time. The Cartwheel Galaxy holds a unique power over the human imagination, its perfect form representing a rare fusion of terrifying violence and breathtaking beauty that resonates on a deeply instinctual level. We are drawn to its symmetry because our minds are wired to find patterns, and here is a pattern on the grandest possible scale, a cosmic bullseye that feels both deliberate and profoundly natural. Its story is a gripping narrative of destruction and rebirth, a phoenix tale written in starlight, making it far more compelling than a static, serene galaxy. This narrative power is why its likeness appears everywhere, from the covers of science textbooks, where it illustrates the dramatic results of galactic collisions, to the backdrop of science fiction films and video games, where it symbolizes ancient, advanced civilizations or cosmic mysteries waiting to be solved. It serves as a perfect visual shorthand for the awesome power of the universe, a single image that communicates chaos, order, and sublime wonder all at once. We see ourselves in its story of catastrophic change and resilient new growth, a mirror of our own human experiences of upheaval and renewal. Why does this one galaxy out of billions feel so familiar, so strangely personal? It is because it reflects our own deepest stories back at us, written in a language of fire and gravity across an unimaginable void. Nested within the grand outer wheel is a smaller, more brilliant circle of light. This is the Cartwheel's inner ring, a structure that presents a mystery all its own, while the colossal outer ring tells a clear story of a propagating shockwave. The origin of this inner ring is far less certain, and its very existence challenges the simple narrative of a single, clean collision. It is brighter and more compact than its outer sibling, a tight band of intense star formation that seems to operate by a different set of rules. How could two such distinct rings of fire exist within the same shattered galaxy? Astronomers are locked in a quiet debate over this puzzle. One compelling theory suggests this inner ring is a ghostly echo of the original impact. Imagine the initial shockwave traveling outward like a ripple in a pond. As it expanded, some of its energy might have reflected back inward from the denser, outer regions of the galactic disk, creating a secondary, weaker pulse. This reflected wave then compressed a separate reservoir of gas closer to the core, igniting this later, more concentrated burst of star formation. It would be the galactic equivalent of a sound echoing in a vast canyon, a fainter but distinct repetition of the original noise. Another, more dramatic, explanation points to the complex choreography of the collision itself. Perhaps the intruder galaxy did not simply punch through and vanish. Its path through the cartwheel could have been a drawn-out gravitational dance, with the smaller galaxy delivering two distinct blows, one as it plunged into the disk and another, perhaps even more disruptive, as it exited out the other side. The outer ring would be the signature of the initial impact, while this brighter inner ring could be the cosmic scar left by the intruder's final, parting gravitational tug. This would mean the galaxy's beautiful form was sculpted not by one strike, but by a 1-2 punch of cosmic violence. The inner ring stands as a permanent question mark, a brilliant clue that the cartwheel's story of destruction and rebirth was even more complex and turbulent than its beautiful, bull's-eye appearance suggests. Our journey through the cartwheel's 50 strangest phenomena is not an ending, but a prelude to a far deeper investigation. These 50 cosmic riddles are merely the foundation, the first layer of a mystery that new generations of telescopes are now preparing to unravel. The James Webb Space Telescope, with its infrared eye, is already piercing the galaxy's dusty veil, peering into the heart of its superstar clusters to witness the very first moments of stellar birth within those dense cities of suns. It can analyze the chemistry of the ring's molecular clouds with a precision we have never before possessed, searching for the complex organic compounds that seem to thrive there against all odds. Soon, the colossal, extremely large telescope will join this cosmic inquest from its perch in the Chilean desert. Its vast mirror will act as an unimaginably powerful magnifying glass, resolving individual stars within the crooked spokes and measuring their motions to finally decode the turbulent kinematics that keep the galaxy's skeleton in flux. It might even capture the faint, distorted arc of a background galaxy, bent by the cartwheel's immense gravitational lens, giving us a new way to weigh its dark matter halo and glimpse an even more distant universe beyond. The greatest secret of the Cartwheel Galaxy may be that we have only just begun to read its story. Each new answer uncovered by these magnificent machines will undoubtedly reveal 10 new questions, pushing our understanding of cosmic violence, rebirth, and the beautiful, chaotic laws that sculpt the universe itself. What unimaginable phenomena we lack even the vocabulary to describe today, are waiting silently within that perfect ring of fire for the right instrument and the right mind to finally bring them into the light. 50 cosmic riddles have unfolded from this single, spinning wheel of fire. We have wandered from its ghostly heart to its blazing ring, from invisible monsters feasting on starlight to the silent, pervasive hand of dark matter. Each phenomenon is a piece of a grander puzzle, revealing how a single moment of chaos can rewrite a galaxy's destiny for billions of years. The Cartwheel Galaxy is far more than a spectacle. It is a cosmic Rosetta Stone, a unique key for deciphering the violent language of galactic collisions and evolution. Its perfect ring is a living translation guide, helping us read the hidden history of our own Milky Way and every other galaxy that was forged in the ancient, crowded universe. This journey is a reminder that destruction and creation are two sides of the same cosmic coin, forever linked in a dance of fire and gravity. We have explored 50 of its deepest secrets, but the conversation is far from over. Tell us which of these strange phenomena captured your imagination. Was it the ghostly intruder galaxy, forever lost to the void, the self-regulating ring of fire, simultaneously birthing and strangling stars, or the silent, ancient red nuggets, galactic fossils hiding in the pale core. Share your thoughts in the comments below, and let's continue unraveling the mysteries of this magnificent cosmic wheel together. So much of the universe remains a mystery, waiting for us to bring it into the light. If this journey through the Cartwheel Galaxy has sparked your curiosity, be sure to subscribe and join us as we explore more of the cosmos's deepest enigmas. And as you look up at the night sky, consider our own Milky Way, a majestic spiral currently on a slow, silent course toward its colossal neighbor, Andromeda. Billions of years from now, these two island universes will meet, and in a blaze of gravitational fury, our familiar sky will be utterly transformed, giving birth to a new celestial spectacle, a future cartwheel written in the stars of our own descendants.